This is an example problem for Physics 1607, Auburn University, fall of 2013. This is an example given in this is a problem from the inter-chapter problems in Chapter 8 in your textbook. And the problem is given as this: a baseball with some given mass m moves to the right with some given speed v1. And then a batsman hits it, a force is applied over some given delta t, and afterwards the baseball moves with a new speed v2 at a given angle theta with the horizontal. So all the given information is listed over here to the right. And we're being asked to find the components of the net force, the x and y components. So when I hear anything about a net force, I automatically think Newton's second law. But as it turns out, in this case, Newton's second law would be really cumbersome to use. We're not given any accelerations, we're given velocities. And in some cases it could be that we could use some kinematic equations and find accelerations, but it's pretty tedious, and in some situations you might not be able to do that. So if you're given masses and velocities, the natural language to use is momentum, and in this case impulse. So what is impulse? Well, your book uses the symbol J. It's just defined here as the change in momentum. And we can also define it thusly: the net force applied over some time interval. And so I'm going to use, this is a simplified definition, I should point out, but for the purposes of this class it's perfect. So I'm going to take advantage of the equivalency of these terms. And notice we're being asked for components of a net force, which I have a net force staring at me right here. So just like in Newton's second law problems, I can break this up into components, and I'm going to use magnitudes as I listed here. So what I can say here is that the sum of the net force in the x direction times delta t equals delta px, where of course p is momentum. And so simple algebra gets me here. And of course I can unpack the delta px term a little bit. So I'm going to have m v2x minus m v1x. All of that is over delta t. Now of course the m's here and here are the same m. The baseball hasn't changed mass, so I can factor that out. Let me go to a new sheet. So I have some of the forces in the x equals m, and I'm going to go ahead and unpack the component velocities. That's going to be mv2 cosine theta minus v1. Of course, v1 is wholly in the x direction, so I don't have any cosine functions there. And all of that is over delta t. So let's check and see. Let me switch colors here. I know this term, I know this term, I know this term. Hello, this term, I know this term, I know this term. Everything on the right hand side is known. I can find that component of the force really easily. I'm going to do the same procedure in the y direction. I'm going to start out with impulse momentum. So, except it's not in the x anymore. Apologies. And notice there are no subscripts on the t. T is not a vector. There are no components. Delta t is the same in any dimension. Equals delta p y. So, if I'm going to, I'll go ahead and follow the same steps. Some of the forces y component equals delta py over delta t. Delta py in this case is pretty easy. You go back to the picture. Notice before the collision there is no momentum in the y direction. There is no, or I should say there's no y component of the momentum. So all I'm left with is the y component afterwards, which is just going to be m times v2 sine of theta. So I'm going to go over here, and this is going to be m times v2 sine of theta over delta t. Again, let me check quantities. I know m, I know v2, I know theta, which means I know sine of theta, I know delta t. All of these are known quantities. At this point, I can plug in numbers, and there you go. Just like that.